This is Introduction to VLSI Design, and today we will talk about CMOS transistor theory. In the outline, we will go through introduction, the MOS capacitor, and then we will see the NMOS and PMOS current voltage characteristic, and then we will talk a little bit about the gate and the diffusion capacitance and why are they important to us. So far we have treated transistor as ideal switch, meaning they could be on or off. If the transistor is on, this means that it is logic 1. If it is off, then it is logic 0. An on transistor passes a finite amount of current. It depends on the terminal voltage, and it is derived from the current voltage relationship or graph. The transistor gate, source, and drain, those are the 3 major terminals, all have capacitance. And those capacitance need to be charged or discharged. According to this law, which is the current is equal to the capacitance multiplied by the change in the voltage over time, or the first derivative of the voltage, which we can rewrite it that delta T is equal to C divided by I multiplied by delta V. And from this, we can read it, or we can get from it that the capacitance and current, they determine the speed. So this capacitance and current, they can get you the difference in time, and because they can give you the difference in time, you can get the speed out of it. Just to remind you, this is the sample of the NMOS transistor. This is the sample of the PMOS transistor. There are also other samples that are used in other books, but mainly we will use this sample for the NMOS and this one for the PMOS. Now we will talk about the MOS capacitor. Remember, a capacitance, to generate a capacitance, you have to have 2 conductors, or at least semiconductors, and there should be an insulated region between those or these 2 conductors. If you have this, then you got a capacitor. So now we have the gate and the body can form a MOS capacitor. And it has 3 operation modes, namely the accumulation, the depletion, and the inversion. So let's see how this works. So first, you can see from here, now we have the polysilicon gate, which is a semiconductor. We have also the B-type body, which is also a semiconductor. And there is this thin isolator, which is the silicon oxide or dioxide. So now in the accumulation operation mode, what happens is the voltage in the gate is 0 or less than 0. In that case, you will have negative charges in the polysilicon gate, and in the B-type, since it is P-type, you have more of holes than electrons, so indicated by these plus signs. Why do we call it accumulation? Because in this region that is right below the insulator, our insulator, it's a region of interest to us that we will call later the channel when we build up the transistor. And since we have positive charges all over the channel, we call it accumulation mode. And then we have the depletion operating mode. And in the depletion region, the voltage, VG, or the voltage at the gate, is larger than 0, but still it's less than the phi threshold, which means you have a voltage at the gate, but it's not sufficient. As an example, let's say that you have a car and your car broke down in the road. And let's say that you and your friend want to push the car away from the road to the side. So what happens? One of you will drive or steer the car, and the other one is pushing the car. If he is pushing the car and the car is not moving, it means that he have this force applied to the car, but nothing is happening. This force was not enough to move the car. Now, at a certain point, when the force is enough, you will advance this threshold, or the force threshold, so you can move the car now to the side. So at this point, the V, like as an analogy to the capacitor, the VG here is not enough to do anything to the channel. Barely it has the region or the channel depleted from the charge, the positive charge. Notice that when you have a voltage more than 0, now you have positive charges in the polysilicon gate. If you compare it to the previous case, there was a negative charge since you didn't apply any voltage. So the negative charge is more than the positive. Now you applied more positive charges because you have voltage larger than 0 in the gate. So you have these plus charges, or you can actually have more positive than the negative in the polysilicon gate region. And this positive charges now is deflecting the other positive charges in the B-type body. And because of this, it's like they are these positive charges are barely enough to just move the positive charges, and that's it. And you have constructed the depletion region this way. Now, let's say that you applied more voltage, and now you are exceeding this V threshold voltage, indicated by more positive charges in the polysilicon region. Now, you don't push the positive charges only, you also attract the negative charges from all over the body to the channel, because now the positive can attract the negative charges because they are enough or more than this V threshold. And now you have what we call the inversion region, or the inversion operating mode. This is if we consider only the MOS capacitance, which is the metal oxide semiconductor capacitor. Now we will try to build up the transistor. So what happens, we know that we have terminals, the source, drain, and the gate. And now between those terminals, you have different voltages. They could be positive or negative, depends on the way you read them. So if you say here VGS from the gate to the source, or VGD from the gate to the drain, or VDS from the drain to the source. These are three voltages that's important to us. More specifically, two of them standing out, which is the VGS, since you care about the difference in the voltage here, because it determines if the transistor is on or off. Also, you care about the VDS. It's standing out because based on this voltage difference, the current in the channel is affected. So If you want to calculate VGS, it's simply VG minus VS. The VGD is VG minus VD. The VDS is VD minus VS. Also, you could say that it is VGS, which is this quantity, subtracted from subtracted from VGD. So by doing this subtraction, you can get also the VDS. You can substitute this value here and this one here, and you will get the same result. So the source and drain are symmetric diffusion terminals, and this is why in our class we are not going to distinguish between them that much. So by convection, the source is terminal at a lower voltage, that's all. And because of this, the VDS is larger than or equal to 0, which means if you do it the other way around in the NMOS, it would be negative. The NMOS body is grounded. That's what we discussed when we talked about the NMOS terminals. So the P substrate is grounded. We first assume the source is 0, 2. So you have a 3-region of operation for the transistor. We have the cutoff, we have the linear, and we have the saturation. We will discuss each one of them by drawing the transistor and looking at it in detail, what's going on in each one of these 3 regions of operation. So let's start with the first one, which is for the NMOS in the cutoff region. So in the cutoff, you can see that VGS minus V threshold is less than 0. So we are taking out this threshold voltage that doesn't do much for us. So if you take VGS and you take out this threshold voltage and it's still less than 0, it means that there is no voltage in the gate that matters. So there won't be any channel here below the silicon oxide. And the current between the drain and the source is going to be 0. You can look at it at the transistor. You can see that this is N plus. So by default, we have more negative charges here. You have more negative charges here. And the body is P-type. So you have positive charges everywhere because there is no voltage applied at the gate. VGS minus V threshold, as we indicated, is still less than 0. So if you see it in this line, for the gate, it's less than 0. So nothing happened in the transistor. And we say that this NMOS in the cutoff region. Now, let's increase the voltage at the gate and let's see what will happen. Now, if we increase the voltage where VGS minus V threshold is now larger than 0, this means that you are starting to form this channel below the silicon oxide. Notice at the simple timing diagram here, now the gate or simple voltage line, let's say. So when the gate when the VGS minus V threshold is larger than 0, now we are moving to this region. Now we can say that there is actually something forming below the silicon oxide. However, there is no voltage applied at the between the source and the drain. So VDS, if we say that VDS is equal to 0, yes, the channel is formed and there is electron there, but they are not moving. So there is no current moving between the source and the drain. And the reason is because between the source and the drain, the VDS is still equal to 0. So now we move to the NMOS linear region, but there is no current flow in the channel. What would happen if we increase this voltage, the VDS, if we increase it? If we increase VDS, we make it more or larger than 0, but not too big. We will come to the too big part. So what happens is you can see that the channel now, there will be current from the drain to the source. It's moving this way. So now what happens, we still have the gate, the VGS minus V threshold is larger than 0, but between the source and the drain, the VDS is larger than 0, but still it's less than VGS minus V threshold. If it is moving, the VDS is still between the 0 and the VGS minus V threshold, we say that the NMOS in the linear region, and there is current flowing between the source and the drain, where if VDS increases, IDS also increases. If VDS decreases, then IDS also decreases. And this is why we call it linear region. So you can see here that the VDS is between 0 and VGS minus V threshold. If we compare it to the previous slide, VDS was equal to 0. So there is no voltage difference, and because of this, no current flow. So now we will increase this VDS more than VGS minus V threshold. So let's see what will happen. And this is what we will discuss next, which is actually the saturation region. In the saturation region, we have VDS is larger than VGS minus V threshold, or we say that it is too big. And because of this, now you can see that the channel is like pinches off. The channel pinches off. And because of this, the current saturated or saturates. So there is no longer a linear relation. And as you can see, this is indicated by the VDS when it is more than VGS minus V threshold. And we say that the IDS is independent of VDS because this current cannot grow any bigger because now the channel has reached its limit. Let's see. Now, these three regions, if we want to put them together nicely in a mathematical model, we do it by introducing to you the Shockley first order transistor model. And it's actually giving you the relationship between the IDS and the VDS, which is actually the voltage and the current within the channel, which really matters to us in transistor. So what happens is we will differentiate between those three regions. We know that the cutoff region is when VGS minus V threshold is less than or equal to 0. Now the linear region is when the VDS is between 0 and the VGS minus V threshold, and the saturation when the VDS is larger than the VGS minus V threshold, and this is what we discussed before. Now to calculate the current in the cutoff, since it's there is no current running in the channel, then the IDS is equal to 0. Now in the linear, the IDS depends on the VDS. So as VDS increases, IDS also increases. And the formula for calculating the IDS is beta time VGS minus V threshold minus VDS divided by 2, all multiplied by VDS. You can say that we have VDS multiplied by VDS, which is going to be VDS squared. So it's no longer a linear relation, but what we are doing here is estimation. And the important part here is that when VDS increases, IDS also increases compared to the saturation region, where you don't have actually VDS in the equation at all. Also, it's good to see that the VGS minus V threshold, this quantity, is showing up in differentiating between those three regions. Also, it shows up in the finding the value of the IDS. Now, for the saturation region, if you want to calculate the IDS, it's beta divided by 2 times VGS minus V threshold all squared. And it's basically, if you substitute VDS by the maximum, which is the limit when VDS is equal to VGS minus V threshold, if you substitute VGS minus V threshold here and there and calculate the linear formula, you will come up with the saturation. So also, if we say that the V threshold is equal to 1 volt, and just so you know, we want the V threshold as less as possible. We don't want the V threshold to be a big number. So if the V threshold is equal to 1 volt, we get this result from a certain transistor, the CMOS transistor, and you can see that as IDS increases, we try to find as VDS increases, we try to find IDS. Now, we did that for 5 different values of VGS. One time we calculated when VGS is equal to 0, and we try to find the relation between VDS and IDS. And you can see that, okay, we go and apply one of these 3 regions, and we find out that the VGS is actually equal to 0. And because it's equal to 0, certainly you are in the cutoff region. And that's why we have this region in the cutoff. Similarly, for 1, you are still in the cutoff. Actually, and when VGS is equal to 1, you are kind of on the edge. But we will assume also this is the cutoff region. Now, as the VGS increases, you have these curves. This is when VGS equal to 1. This is when it is equal to 2. This is when it's equal to 3. And here, when it is equal to 4. Now, you can see that these parts here, when the VDS saturate, is the saturation regions. So you have the saturation region here, 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 and also there. This is why we say that all of these regions here, this is the saturation. Even if you choose VGS 3.5, for example, you will have the saturation somewhere here. The linear, you can see that it's not a straight line, but there is a relation. As VDS increases, IDS also increases. See, you have these curving for each one of the VGS values. So we can say that this region here is the linear. Here we have the saturation, and really below we have the cutoff. Now, of course, to find this, we apply these values, and we need to know what is the beta value. So it's good to know that first, that this quantity, the VGS minus V threshold, it's called the VD saturation. So the VD saturation is equal to VGS minus V threshold. Now, to calculate the beta, it's equal to mu, which is the mobility of the electrons. Since we have NMOS transistor, we have mu N for the electrons and mu P for the holes. So mu, supposed to be mu N, since it is an NMOS transistor, times the the capacitance on the oxide, which is here. This is our silicon oxide, and times W divided by L. Now, the W means the width of the transistor. So this is our W. And L is the length of the channel. Now, to get the capacitance, now you can see that the capacitance, and remember what we talked about the capacitance and the region of the capacitance of the operating modes. Now, the capacitance at the oxide is equal to epsilon oxide divided by the thickness oxide. So you have this thickness oxide here, the thickness of the silicon oxide region. So C oxide is equal to epsilon oxide divided by the thickness oxide. And this epsilon oxide is equal to 3.9 epsilon naught. And epsilon naught is this quantity, which is for air. This is for air, which is 0.85 times 10 to the minus 14 farad for every centimeter. This is for air. Now for silicon, it's 3.9 times this amount. Okay. Now we said before that we were able to generate these curves. But how exactly? Since we introduced to you the way of finding the beta value, this is what we are going to do in the next slide. You have an example. We will be using 0.6 micrometer process. Actually, even for the project of this class. If we say that the thickness oxide is 100 angstrom, and we mentioned this before, that it is actually 100 times 10 to minus 8 centimeter. And if we say that the mobility is 350 centimeters squared per voltage times second, and we say the V threshold is 0.7. Now, I gave you the values that you really need to calculate the beta, except the W and the L. Now, if I said plot the IDS versus the VDS for VGS equal to 0, 1, 2, 3, and 4, and also 5, you can draw it by first assuming that the W divided by L is equal, let's say 4 divided by 2 lambda for the NMOS, which was the conclusions that we reached in the last slide in the previous video. So if we say this, we could say that we can find beta since I have mu, and I can find the silicon oxide, which is 3.9 times the constant that we said, divided by the thickness oxide, which you have given to you. So now we find the capacitance at the oxide and multiplied by W divided by L. You could say that it's equal to 2. You can apply these values and you will find that the beta is 120 multiplied by W over L, or it's multiplied by 2, so it's 240 micro microampere divided by square of the voltage. So all the IDS and VDS are variables, and you draw it using tables like what you studied in high school. And you assume the values of the VDS, which is in the x-axis, being 0, 1, 2, 3, 4, and 5. So you have 0, 1, 2, 3, 4, and 5. And you try to find the value of the IDS. Now, since VGS is equal to 0 for this first table, IDS is going to be in the cutoff region the whole time, so it's 0 for everyone. And now you generate the first curve, which will be actually in the line of the x-axis itself. Now you get it for the next one, which is when VGS is equal to 2 and 3 and 4. For example, when GVS is equal to 5, you will assume the VDS again from 0 to 5, and you find the IDS by applying the first degree Shockley model, or the first order Shockley model, which is this one. So when the VDS is equal to 0, this means that the IDS is equal to 0, which is this point here. Now it is equal to 1. It means that you will apply the linear relation, which is this one here. So you will, beta, you already find it. The VGS minus V threshold, the V threshold, you already have it. And the VGS are given to you is equal to 5. And you have the VDS, which you assumed. You assume now it is equal to 1. And from that, you can find the IDS. So you get it 1. If you have VDS is equal to 2, the only thing that is changing is the VDS here is equal to 2 now. You get 1.6, and every time you find pair, you put a dot in the curve. You have this 1 and 1, so this is 1 and 1. You should put a dot here. So you have to put dot here, you put dot here. 2 and 1.6, this is 2, and this is kind of 1.6. And 3, 2.1, 3, you have 2.1. And 4 and 5, you notice that you are actually moving from the linear region to the saturation region. So you apply this rule, because VGS minus V threshold is, or the VDS is larger than or equal to VGS minus V threshold at 4 and 5, when the VGS is equal to 4 and also 5. So at that time, you can find the value, but when the VDS is equal to 4, the IDS is equal to 2.3, and the 5 also 2.3. And now you can draw the curve by connecting these dots. This is the way you draw it by hand. There is also simulation tools that can do this for you easily. Or a programming language like MATLAB. You can plug in the equation with the given values, and it could draw it for you. Now for the PMOS, one thing that you need to remember that the relation between the mobility of the electron and the mobility of the hole. So the mobility of the electrons, which is mu n, is equal to twice the mobility of the holes. And the reason of this, when the electrons are the one that is really moving, and the holes is the after effect of the movement of the electrons. And because of this is slower than the electrons. And this is the relation between mu n and mu p. If you want to draw what we discussed for the NMOS, if you want to do the same for the PMOS, you will have the curves like this. It's like in the third quarter of the XY plane, where the VDS is negative values and the IDS is also negative values. Now for the capacitance, any capacitance, as we mentioned, that it is any two conductors separated by an insulator. We have the gate to channel capacitor, which is very important because it tells you if the transistor is on and off. It creates channel charge necessary for the operation, meaning being off, on and off. You have another capacitance which is between the source and the drain. And this is also important to us. And it's across the reverse bias diodes as well. It's usually called the diffusion capacitance, where the first one called the gate capacitance. So you have two types of the capacitance. We have the gate capacitance, and we have the diffusion capacitance. And they are, in this figure, this is the gate, and these are the diffusions. Here we have the diffusion capacitance, and here, vertically, we have the gate capacitance. As you can see, you have two conductors or semiconductors between an insulator, and here, if the channel is off, even if it is on, you have two conductors in a certain direction between an insulator if the channel is in the cutoff region. And as the channel is progressed, you have certain relation between the source and the drain. So it's the gate capacitance. Here we will say that the gate capacitance approximate the channel as connected to the source. So you have the CGS equal to epsilon oxide times the width times the length divided by the thickness oxide. And we said that the epsilon oxide divided by the thickness oxide is what we call the capacitance at the oxide. And now this capacitance, if we multiply it by the dimension W times L, we have the overall capacitance. We could say that since L doesn't change much in every generation, we usually change the W. Actually, both of them changes, but in a certain generation, the L never changes, but the W changes based on the transistor and how you are connecting them. Are you connecting them in series or in parallel? So the W changes, but L is fixed if you know your current generation. And because of this, we get those two together and we call them C per micron times W. And this is key result. Now, the capacitance at the gate, CGS, is equal to a constant per generation times the width of the transistor. So the width of the transistor is telling you how much is the capacitance. And this is what we say. We can simply say that the C gate is equal to C per micron times W, and the C per micron is typically about 2 femtofarad per micrometer in all processes. And as we progress through the class, we will show you some cases where you have certain C per micron for each generation. Now, this is about the gate, calculating the gate capacitance, which basically it is based on the width of the transistor. What about the diffusion capacitance? The diffusion capacitance, it's from the source to the body, or from the diffusion to the, or from the drain to the body. It's undesirable. It's called parasitic capacitance. And whether you like it or not, it's always there. It's one of the inherited properties of the transistor itself. So the capacitance depends on the area and the perimeter again. So you use small diffusion nodes, you compare to the what we calculated in the gate capacitance. And we would find that this capacitance, the diffusion capacitance, will be equal to the C gate or half the C gate. And the C gate, or the capacitance at the gate, we said that it's C per micron times the width. When is it going to be equal to C gate, and when is it going to be equal half the C gate? It's based on the how are you modeling your transistor in the layout or in the stick diagram. So we have three cases here. We want to differentiate between them, and then we will come to this. First, if you have two pulleys, remember, for example, this circuit, we discussed this before, and we say that this is 3 transistors in series. If we say that this is A, and this is B, and this is C, so we have A ANDed with B, ANDed with C. I'm looking at the pull-down network here. And we will say all bar, and this is our output or our function. If we say that this node here is the function F. So now we found the functionality of this circuit. From this, we know that this is a 3-input NAND circuit. So that's a real layout of a circuit that we know. If you looked at the layout, sometimes we have two pulleys and there is nothing there between them. So we say that this is a merged uncontacted diffusion. So the diffusion is merged, meaning that this is the first transistor and this is the second transistor. So let's do it this way. If that's the first transistor and you have N plus here, and you have N plus here, since it is in MOS, the second transistor is using the same diffusion here. So we don't have another one for it. This is why we call it, it's uncontacted because there is no connection in this diffusion. And also it is merged diffusion or shared diffusion. Some people like to call it shared diffusion between the two transistors. So it is here and also here. In that case, we will have the distance here 3 lambda. Because we say that here it's 2 lambda and we need 1 lambda here. And we have another lambda over there. And the spacing between them, 1 lambda. Now, what if we have a shared diffusion and also contacted? In that case, we have a contact between those two. They are shared. We have a single diffusion, but it is contacted. It is connected to some other metal wire. And because of this connection, we need to have a contact. Now, the contact, we say that it is 4 by 4, meaning that this side is 4 lambda. And we have 1 more here and 1 more here. So the total is 6 lambda. In total, 6 lambda. That is if it is shared diffusion. And this is usually the case. When we have a contact, we assume that it is always shared. Now, what if we make them isolated? It's not shown here, but if we make the contact, well, actually this one is isolated here. If we make the contact isolated, then you have a contact 4 lambda here and 1 more here. So 4 and 1 is 5 lambda. And you have the same here. So you have another 5 lambda and you have the spacing between them as well. That is if you do it as an isolated diffusion. But in design, we don't recommend this. We usually either have a shared diffusion or that is contacted or not contacted. If they are contacted like this one, then the capacitance is equal to the C gate. So the diffusion capacitance is the same as the gate capacitance. If they are not contacted, then it is half that amount. And you can see the relation between 6 lambda and 3 lambda, they are halved. And this is why we have these relations. So as a conclusion, the gate capacitance and the diffusion capacitance, they are the same if the diffusion capacitance is contacted. So after discussing the relationship between the current and the voltage and writing the mathematical model, which is the Shockley model, where it has the cutoff and the saturation and the linear regions, that was the ideal case. So this mathematical equation here is the ideal relation between the current and the voltage. However, we have actually a non-ideal transistor behave because of many effects, like the high field effect. And because of this, you have mobility degradation and velocity saturation. Like, for example, if you have this, and because you have a high electrical field, which is the lateral field here, EL, and also you have a vertical field, the EV, because of this, those electrons have collisions, they are slowed down, they hit the silicon oxide. There is so many things that are going down here because of those two electrical fields that cause mobility degradation and velocity saturation. Also, you have channel length modulation effect. And as you can see here, you have the length that you assume between the two diffusion regions, but it's actually less than that, what we call the effective length. We have also threshold voltage effects coming from the body, coming from the drain, and coming also from the short channel that we discussed, or that we just mentioned here. We also have leakage effect. The current is leaking out. As an analogy, if you have a water tap and you didn't close it all the way, you could have drop of waters leaking from the faucet. Similarly, for the current, you could have leakage in 3 regions, actually more than that, but these are the standing out region: the subthreshold leakage, the gate leakage, and the junction leakage, indicated by this figure. This is the gate leakage. You know that there's not supposed to be any current going from the gate to the rest of the transistor. But because of this leakage behavior, there is actually a very tiny current leaking out from the gate. We call it the gate leakage. Also, you have a subthreshold leakage that's in the opposite direction of what you want. This leakage is not, we don't want it, we don't like it, but it's there no matter what we do. So that's the subthreshold leakage, and you can relate to what we discussed to the electrical field here. The lateral electric field, it is having leakage as well. The vertical leakage, the vertical electrical field has leakage current as well. We have also the junction leakage. If you remember the B-in junction that we discussed before, there's supposed to be a certain direction of current. There is an opposite current in the direction that you're not supposed to have. And it's all the way through the diffusion here and also here. This is what we call the junction leakage. So we have leakage of the current. We have threshold voltage that are affected by many factors. We have degradation in the velocity and the mobility of the electrons. We have a shorter length of the channel. All of these are non-ideal, these are effects that cause what we discussed, which we call the ideal transistor theory, or the relation between the current and the voltage. They make it non-ideal. These effects is actually internal in the transistor itself. There is also an external effects, like the process, the environmental variation, for example, the temperature and the voltage that you apply to the gate. Now, what happens in the non-ideal case? The black lines here is actually the ideal transistor theory, or the ideal relation between the VDS and the IDS. Now, when we do the real thing, or we simulate it in a good simulation that is mimicking what's the real transistors, we can find out that there is a huge drop from the ideal case to the non-ideal case when VGS is equal to 1. If you want to compare also 0.8 or 0.6 or any other value, you can see that there is a strong drop because of what we discussed. Some of them are mentioned here in the figure, like the velocity saturation and the mobility degradation make the ion lower than the ideal model predicts. Also, you have the velocity saturation and mobility degradation saturation current increases less than quadratically with the VGS. So it's quite the reduction, which is surprising now to you in the non-ideal case. Similarly, you have this slope. In the saturation, it was saturating, and that's it. It's a straight horizontal line. Now we have kind of a slope here. And this is because of the channel length modulation. Also, the saturation current increases with the VDS. This is some of the non-ideal effects, and you can see that it's affecting the operation of the transistor. Next, we will talk about the DC and transient response of transistors, which is the next step after knowing the transistor theory.